So homework number 2, problem 6, we have a surface mount inductor, and the inductor has a self-oscillation frequency of 12.4 gigahertz. And this self-oscillation frequency is measured if we short one port and measure the impedance from the other port, right? And basically, the self-oscillation frequency, a self-resonant frequency, is determined by the combination of L and C, right? So what I can do is first, I can simply calculate what's going to be the C value required for this 12.2 gigahertz. So I'm going to switch to MATLAB first, write a very short script. I have inductance of 1 nanohenry. And our frequency, self-oscillation resonant frequency is 12.4 gigahertz, right? And if I have this frequency, omega equals to 2 times pi times f. And with that, I can calculate C. C equals to 1 over L over omega squared. Is this right? Okay, great. So that's how we calculate the capacitance. And I'm gonna save this script on my desktop, class demo. All right, I run the script. And after that, it tells me the capacitance will be 1.647 times 10 to negative 13 farad. All right, so that's how we determine the capacitance. And in order to determine the resistance, we have to look at the Q, and we are told that the Q quality factor equals to 60 at 800 megahertz. So I'm going to switch back to MATLAB. Now we are talking about Q. Q is 60, and the frequency measured at 800 megahertz, right? We have the same inductance, 1 nanohenry. So resistance should be L times omega divided by Q. Does this make sense? That's the definition of the resistance, right? And I have to update my omega. Omega equals to 2 times pi times f. And in this case, f is 800 megahertz, right? So run the script again. I get the resistance 0.0838 ohm. Okay, so with those two values, I'm gonna switch to AWR. So if you are using a Windows computer, that's the best scenario. You just install AWR. And if you're using Mac, you have to install a virtual machine first. Then we're gonna load AWR environment 11. And if you run it for the first time, it's gonna ask you for the units of the design. You can either select millimeter or mils, depending on which way you prefer. Okay, so after you select the units, you come to this screen, and last time we learned that we can create a schematic, right? How do we create schematic in AWR? Go to project, is this right? And I can do add schematic, new schematic. I'm gonna name this schematic as homework 2. Create, all right? And once we get this schematic, I'm gonna put the components on the schematic, right? So I can go to elements. So on the left side of the window, you have 3 tabs. You can choose project. This is a project manager with the schematic, the simulation results, and the second tab, elements, where you can get the elements for your schematic, right? So we need inductor, we need capacitor, and we need resistor. All of them are numped elements. So I'm gonna expand numped elements and click on inductor. And we have lots of inductors because we may have surface mount inductor, we may have on-chip inductor, we may have bound wire inductor, right? So you may have a different model. But for this homework, we are gonna use the most basic inductor, IND, so ideal inductor, okay? So if I drag it towards the right-hand side, I'm actually moving the placing the components to my schematic. Okay? Do you have any questions so far? If I'm going too fast, let me know. I can slow down. Okay? And feel free to ask me questions. It's very helpful. All right, so we need the inductor here. What else do we need? Capacitor, right? Resistor, okay? I heard resistor. So I'm gonna click resistor here. RES, that's resistor. I'm gonna drag it into the schematic. And do we still remember what is the size of the resistance? 0.0838, okay? So I can double click the R value here and I enter 0.0838. That's the resistance, parasitic resistance, all right? And if I want to move around on the schematic, I can use the arrow, like left side, right side, just use your keyboard. You can move around. And besides the inductor and the resistor, what else do we need? Capacitor, yes, thank you, capacitor. I'm gonna put a capacitor here into my schematic. And now the capacitor is horizontal. If I want to rotate it, let's guess, what can I do? Right click, okay? So if I right click, then it's rotating the component, okay? If you don't want to right click, then you can do Control R. Like you select the component, Control R, then you click on the component, drag the component, and you can also rotate it, all right? Very simple. And what is the size of the capacitor, please? 1.6474 times 10 to negative 13, okay? So if we are using a unit of micrometer, then it's gonna be 1.6474 times 10 to negative 7. Is this right? Okay, so 1.6474 times 10 to negative 7, all right? And I need to, and the font, the character is overlapping with the symbol, which is not very good. I can actually drag it outside to make it look better, a little bit better, right? And after that, I'm gonna select this capacitor, and I'm gonna use Control C. Yes?
Okay, so we have picofarads, I would use microfarads. Does it click on it more?
I think you can, yes, you can. So if you, let's see. Yeah, right here you can change the unit, okay? So either way works. You can change the unit to picofarad and change the number, or you can keep the microfarad and use, just use 10 to negative 7, okay? But anyway, the point is microfarad is 10 to negative 6, and you have 10 to negative 7 on the number. So in total, that's gonna give us 10 to negative 13, okay? Does this make sense? All right, great.
It's not letting us change it for some reason.
Oh, you can change it?
You can just change it.
All right, doesn't matter. If you can change it, then just change the number. All right? Okay. So after that, I'm going to copy the capacitor to create another one on the right-hand side. Okay, does this make sense? I'm going to copy the capacitor to the right-hand side. Okay?
Are you copying?
Control C is copy and Control V is paste, just like you did in Windows, okay? All right, so this is a very nice software. It's light, small, not as large as ADS, but it's powerful. It can do pretty much anything you can do in ADS. And another good thing is the commands are very similar to Windows. So if you are good at video gaming, then basically I don't think you have any problem with the design. Okay? And another trick is now the screen is pretty small, right? I'm gonna move my mouse to the top side. See here we have a button View All. If I click View All, then everything will be fit into the screen, okay? You can also zoom in, zoom out. I guess any Windows software looks like this, right? Pretty easy to handle. And now we're gonna add a wire. So just move the mouse to the terminal, and automatically you see we get a wire, right? And I'm gonna click it and drag it to the other side, make a connection. So now we get a very good connection. All right. And remember, this software is free to universities. And after you graduate, you can still use it for free in a company for 1 year. That's a very big advantage during like interview. You can tell your company you can bring them this software, right? Okay. So I also clicked this button to add the ground. Okay. Does this make sense? You can add the ground. All right. After that, I'm gonna add the 2 ports for the simulation, because remember, if we look at the problem, we have 2 ports, right? So moving back to AWR, on top side, we have this button. Do you guys see it? Yeah, this is port. So click port. I'm gonna place the port here. I'm gonna place another port. I'm gonna rotate it and place the other port on the right-hand side. And I'm gonna fit the screen again and add the wire connection. Okay. So everything is so simple. And just in case Windows is not robust, it's gonna crash sometimes. So save the project, right? Click save, and I can name the project as class demo Spring 2015. Click save. Okay, and also remember where you saved it. All right, and now we have the schematic. Intuitively, what do you think is gonna be the next thing we have to do? I want to simulate the impedance to confirm the set a frequency. Okay. What else? Set a frequency. That's a good answer. Anything else? I've got to tell the software what to simulate, right? Okay, center frequency is 2.4 gigahertz. We're gonna do frequency setup later. So the first thing, a little bit special for AWR, is to tell the software how to do simulation. You actually do it through the plot, because eventually the simulation will show up as a graph, right? So I move to graph. If you look at the left side, the list here, we have a folder graph. I'm gonna right click it and select new graph. And I'm gonna create a graph with the name similar to my schematic, which means this graph is gonna plot the simulation result for this schematic, okay? But you can name it in your own way. You can use a different name. And as we can see, there are different types of graph. You may have 3D plot if you are doing 2.5 EM simulation. You may have histogram, you may have polar graph, you may have Smith chart. But today we're gonna look at the simplest rectangular graph, okay? After I click this, I have this graph generated, okay? A very nice graph. And I highlight this graph on the left-hand side on this panel, and right-click it again, and I'm gonna click Add Measurement, because I have to tell the simulation what kind of measurement I'm gonna add. Does this make sense? Okay. So if you look at the simulation, its measurement type is pretty complicated. You can do EM simulation, you can do linear simulation, you can do nonlinear simulation, you can do load pool simulation for power amplifiers, all right? And again, today we're gonna start from the simplest. For S parameter impedance, those are all standard linear circuit analysis. So we're gonna do linear simulation, all right? And under linear simulation, we have port parameters. We simulate the impedance, the S parameter, the transconductance, things like that, okay? So make sure you select linear and the port parameter. And if we're gonna simulate for the impedance, intuitively, let's guess, which one should I choose? Y or Z or G or ABCD? Definitely Z, right? Very intuitive. And here on the right-hand side, we have data source name. If I click this, I have a drop-down list, and now I only have one file, homework 2. Okay, so can we guess what is the function of this guy? Yeah, it tells the simulator which schematic I'm simulating, because eventually I may have multiple schematics under this project, right? So I tell the simulator I'm gonna simulate for homework 2 schematic, and now we have port 1 here, and I'm gonna simulate for port 1 the impedance, all right? And I'm gonna plot the real part and imaginary part of the impedance. Does this make sense? Okay. So going to the bottom side, I'm gonna select real part, and I'm gonna click apply. Then if you look at the graph, you have real part of Z11 added to the graph. Okay. And would you please tell me what does the RE mean? Real part. Great. How about Z? Impedance. How about 1, 1? Port number 1. Okay. And I also want to plot the imaginary part. So click imaginary, click apply, add the imaginary part. All right. So after that, we have schematic, we have measurement. What else are we missing? Simulation. Simulation is actually set up through the measurement. I told the software I'm going to measure this, which means I'm going to simulate for this. But somebody actually mentioned this before. Frequency, right? Go to project, and go to option. Under option, we have project options. Okay? So let me do it again. Go to option on the top and select project option. And here you can enter start frequency, stop frequency, and step size. Okay? So let's say our problem, this guy has a self-resonant frequency of 12.4 gigahertz. So I'm gonna check out the performance around 12.4 gigahertz. All right? So I'm gonna start from 10 gigahertz, end up with 14 gigahertz. So the center frequency will be very close to 12.4, right? In step frequency, it's gonna be the work of a computer, so I don't care. We can make a small step size. The computer is gonna be tired, not me. So step size is gonna be 0.01 gigahertz, okay? And after that, a very important thing, remember, you have to click this apply. If you don't click apply, this setup does not apply to the simulation. So if you click apply, look at the window here. All the frequency points are populated into this window. Okay? Any question? No? Great. So if no question, I'm gonna click OK, and I'm gonna move to this button, Analyze. So if I click Analyze, the simulation is done very quickly. Okay? And now if we check out the simulation result, imaginary part, the resistance is changing from negative to positive. At this frequency, it's 0, which means resonance happens, right? And for the real part, we have a small number, all right? Okay. Let's see. Oh, I made a mistake. I made a mistake. What mistake did I make? If we have to measure the quality factor, measure the self-resonant frequency, what am I missing? We have 2 ports, right? We have to ground one of the ports, right? If we measure from port number 1, I'm gonna ground port number 2. Okay, so we have to add this ground, and that will give me a more reasonable simulation result. Run simulation again. Oops. Did I do anything wrong? All right, let me double check. Oh, what a bummer. So let's do this. Since I only have to measure at port number 1, I'm gonna temporarily remove port number 2. Okay? Not sure what happened, but let's try if I can get this fixed. Okay? Temporarily remove port number 2 and see. I'm gonna reset up the simulation. I'll delete this. Okay, and from the graph, add measurement, simulate for z parameter, add the real part, add the imaginary part. Okay, and now run the simulation. All right. Yeah, here we go. Okay, so it's embarrassing, but it also shows that we can definitely debug problems, right? Okay, let me understand it as a good thing. All right, so if we look at the simulation results, I think this makes a lot more sense because looking at the real part is gonna peak at this frequency. Okay, you have a parallel resonant circuit, then definitely the impedance is gonna peak, right? Real part is gonna peak. And if you look at the imaginary part, then for the imaginary part, you have a positive imaginary part before resonance happens, and you have negative after resonance happens. And at a resonant frequency, imaginary part is just 0. Okay? All right. Do we have any question? Yes. How did I get a spike? So basically, you have to short the second port. Okay. If you short the second port is of no use, and I removed it. Okay. So now this is a true setup to measure the resonant frequency. Does this make sense? Okay. And with this, I set up the same measurement. I'm gonna measure the z parameter for homework number 2 schematic at port number 1. Okay, and I'm gonna plot the real part and imaginary part. I added the real part and imaginary part. Okay, so anybody can repeat and get the same result. Yes. Okay, great. And different results. No? Okay, great. So I'll assume that we are okay on this, although I actually screwed up a little bit. And now another thing I want to show is on the graph. Yes?
If we remove the, we have removed the port 2,
Uh-huh.
we have routed the thing.
Right.
If we don't connect the port 2,
Uh-huh.
we have removed the ground,
Mm-hmm.
and we are checking only port 1,
Uh-huh.
we get the different result. And can I know the reason why?
Actually, when I did the first simulation, I forgot to ground port 2. That was why we had different results. I forgot to ground port 2.
I have removed this wire and ground
Uh-huh.
and simulated, and I'm getting different.
So are you saying that if you add port number 2 here?
Remove that wire.
Right, you can't remove this wire because you have to ground port number 2 in order to measure the resonance. Okay, if you don't ground it, you're actually leaving one of the port open. Port number 1 you have the source, but port number 2 is left open. Okay, and you have a more complicated resonant network. All right. Okay. All right. The last thing I want to show is from here. Sometimes you want to like mark and tell others the simulation result, right? So what you can do is you can go to graph, marker, add marker, okay? And you can add a marker here. And as we can see, at 12.4 gigahertz, let's see, you can read out the value, okay? So the value will be very close to 0. Let me zoom in a little bit. Project option. I'm gonna do it from 12 gigahertz to 12.8 gigahertz. Zoom in to look at more details. All right.
Press apply.
Yes.
You forget to press apply.
Oh,
For the frequency.
okay. But it's actually updated. I clicked it. All right. Okay. So now, as you can see, around 12.4 gigahertz, you indeed have a very small value of the imaginary part, right? And if you move a little bit further, you have a much larger value. Okay. And you can also add the marker. So go to Graph, Marker, add marker to the real part. Okay. And from the real part, you can read out what's going to be the impedance, real part of impedance at a resonant frequency. All right. Okay. And if you want to make the plot smoother, then you can further reduce the step size. And if you further reduce the step size, you're gonna have a better curve, right? Okay. But I wonder why the reading does not. Let me remove this marker. I'll do it again. Yeah, so if we get very close, then you can see the imaginary part will become close to 0, right? But I don't have a mouse, so I can't precisely locate at a 0 cross point, okay? Yes.
You can do a search on the marker.
Okay. How do I do a search?
You just right click on it and marker search.
Okay. Marker search. Okay, thank you. And search for value of 0. Yeah. So thank you very much. So that's a very nice trick. If you do a search, right click on the marker and do marker search. You can search for value of 0. And after that, you will see the frequency is exactly 12.4 gigahertz. All right. Any question? No? Okay, great. Any comment? No? Okay, great. So if no question, then I guess pretty much that is for homework number 2. And the next example we're going to have is to run some transmission line simulation. So to do that, I'll go to Project, add Schematic, and add a new schematic. And this time, I'm going to do T-line simulation. Okay. So on the T-line schematic, I can add transmission lines. Okay. So if you look at element list, you have microstrip, which is a realistic transmission line, but you also have, I guess, ideal transmission line. So here we have transmission line. If I expand it, we have different types of transmission line. You have coaxial. You can specify transmission line by phase, or you can use the physical size to specify the transmission line, like the width and length and the substrate, right? So today we are going to do a very simple demonstration. We're going to do phase. And from phase, I'm going to use T-line, the most fundamental type of transmission line. Okay? So I place this transmission line there. And the example I'm going to do is I'm gonna do a quarter wavelength impedance conversion. Okay, so let's go to our transmission line lecture. Transmission line lecture number 6. And for lossless transmission line, if you still remember, we had several special types, and one of the special type is called quarter wavelength transmission line. Okay. And basically, if the transmission line length is quarter wavelength, then you can convert the load impedance to a different value based on this equation. All right? So let's say if I have a 50 ohm transmission line and my load impedance is also 50 ohm, what's going to be the input impedance? Still 50 ohm, right? Okay, so we're going to do this first. I have a transmission line there. For lumped elements, I can add a resistor So I'll drag this resistor into the schematic and rotate it by right-click it. Okay, and I'm gonna put a 50 ohm transmission line, a 50 ohm resistance, ground this. Okay, and wire it. Add port number 1, and make a connection. All right. Any question? So actually, there is a big question. If we look at our lecture note, the transmission line normally we have 2 sections. One is for the signal path and another is for ground, right? But for the simulation, many times you can only use one section like that because basically the bottom one is always grounded, okay? So you can use a simple model like that. But if you want a model somehow exactly the same as this, that's also possible. You can choose, so if you go to transmission line, phase, and you can choose this guy, okay? If you use this guy, then it's gonna be exactly the same as what we have on the lecture note, okay? All right, so today we're gonna use the simpler version, and EL here represents electric length. And for quarter wave length, lambda over 4, the phase corresponds to 90 degree, right? So electric length will be 90 degree. All right, does this make sense? Okay, I'm gonna add a plot. So add a new graph, and on this new graph, I'll add a measurement. And again, I'm gonna measure the Z, the impedance. But now, remember, we have to simulate for the T-line schematic, right? So this is an important change, changes to T-line, okay? And I'm gonna plot the real part. I'm gonna also plot the imaginary part. All right? Okay, yes?
You had a new, so you switched to graphs and added a new graph, right?
Say it again?
You added a new graph for graphs.
Right, I added a new graph. So from graph here, right click and choose new graph. Okay, you can also rename the new graph. Okay, but I just didn't do that. All right. So after that, another thing I want to demonstrate is for the frequency simulation, I can actually pinpoint to a single frequency. Okay, let's say if I do simulation only at 1 gigahertz, click apply, okay, do it at 1 gigahertz, and then run the simulation. And after simulation, as we can see, the imaginary part has a value of 0, and real part has a value of 50. All right? And if you want to confirm, you can add a marker to the real part, and it reads out as 50. Okay? Does this make sense? All right. And next, let's say if I short the load side, if ZL equals to 0, tell me what's going to be the input impedance after the quarter wave length transmission line. If ZL is 0. Plug into this equation. That's going to be, our Z0 is still 50, right? And ZL is 0. Then, yeah, input impedance will be infinity. You are converting a short circuit into open circuit, right? So we can confirm the same thing. I'm gonna short this end and run the simulation again. And after the simulation, the real part, wait, let's see, add the marker to the real part. How come the result is 0? Let's debug, okay? We have a quarter wavelength transmission line, right? The load is grounded. And, but we have imaginary part, okay? So check out the imaginary part Let's go to graph, marker, add a marker. Oh, okay. So see, that's a problem. That's a big problem. Do we see any problem here in the simulation? The 90-degree is given for the transmission line working at 10 gigahertz. Is this right? And what is my simulation frequency? That's only 1 gigahertz. Okay, does this make sense? All right, so at 1 gigahertz, that's definitely not a quarter wavelength transformer. Okay, so that's a problem. Go to options, project option. I'm gonna change the frequency to 10 gigahertz. Click apply and run the simulation again. So after the simulation, as we can see, we have a huge imaginary part, which means it's pretty much open circuit. Okay, does this make sense? All right, and we can do another example. I'm gonna now leave this port as open circuit. Leave this port as open circuit. If it's open circuit, would you please tell me what's gonna be the input impedance after a quarter wavelength transformer? 0, right? You are converting open circuit into short circuit. So run simulation again, and you can see the number here is almost 0. Very, very small. And actually, it's actually due to numerical error. So the answer is pretty much a short circuit. Okay? Any question? No? Okay. If no question, then the third one is parameter simulation. So we can go to project, add schematic, new schematic, is parameter. All right. And for is parameter simulation, what we can do is, let's see if we have any example to do. So let's look at our is parameter lecture note. All right. So for is parameter lecture, we had an example. We have a pi network, right? We have 100, 100, 100. And after calculation, we figured out what is the S11 and S21. Okay, answers are there. So let's try if we can verify this using simulation. So go to elements. I'm gonna add the resistors. Okay, and drag this resistor into the schematic and change the resistance into 100 ohm. And I have to copy this resistance, make a pi network, okay, like this. And I have to ground this one and also ground that one. And make a connection from here to there and also from here to there. All right. And I'm gonna add, now we have 2 ports, port number 1 and port number 2. Okay, make a connection for the ports. All right, so with that, we've got our setup of S parameter simulation. Okay, so now we have to, what's next if I want to set up the simulation? Go to graph, and I want to right click and add a new graph. Again, I'm gonna use rectangular graph, okay? And for this graph, I'm gonna add a measurement. So add measurement, and now we are not simulating the impedance, we are simulating for S parameter, okay? All right, and for the schematic, I have to change it to S parameter schematic. And I have to plot the real part together with the imaginary part of S parameter. And if you look at the result I added here, it's S11, S11, because we have 1 here as 2 port index and from port index. What if I want to plot S21? S21 means the transfer from port number 1 to port number 2. Is this right? So we're gonna start from port number 1, but here change it to 2, which means transfer from port number 1 to port number 2. And we're gonna add the real part, we're gonna add the imaginary part. Okay? And after that, let's see if I have to set up the frequency. Oh, because this is a flat system, there's no frequency selective component. It doesn't matter which frequency we are simulating, right? So I simply run a simulation, and after simulation, I got a whole bunch of results. And from here, we can interpret the imaginary part of S11, imaginary part of S21 are both zeros, which makes sense because our calculation tells us S11 and S21 are both real numbers, right? And I can add a marker to check out the value for the real part. So if we add this marker, we can see this guy is S21, right? Real part of S21. It has a value of 0.2667, and our calculation also tells us S21 is 0.2667. And for S11, the value is 0.06667, agrees with our calculation result. Okay? All right. Does this make sense? Okay, great. So I think that's pretty much all for the AWR simulation. Do we have any question? Very simple, right? Except that I made some stupid mistake, but I guess you guys will have no problem on that, right? Make sure frequency is correct and the port you treat it correctly. Okay, all right. So now I have to stop this. How do I stop this? Never mind. I'll stop that later. We still have 3 minutes. Do we want to talk about the project or you guys want to go home? I want to talk about the project. Okay. So you can download several slides from MIT website, which is very helpful. Okay. And among them, what I'm gonna discuss is for this slide, it's pretty much overview. And it's for really lazy people. It has step-by-step guidance to build up everything, even the photos, okay? So definitely, I don't think we have any problem to repeat and get the same system, except you may have a different color for your coffee can, okay? But that's not enough. If you want to impress the class, then you want to make a better job, right? And the easiest way I see is, if we look at the design, those are bulky breadboard. One simple thing we can do is we can integrate everything together on a green board. That will also make the performance better. You can shield out a lot of interference and noise, right? So that's definitely what you can consider. And basically, you have a radio frequency chain, transmitter and receiver, and after that, you have baseband signal processing, okay? And so this is one of the slides. And another slide, number 3. This one talks about the RF system here, okay? So it explains how the RF system works. And we also learned this in our class. We have oscillator, this guy. We have amplifier, this guy. And we generate the signal, and we have to split the signal into 2 paths. One is transmitted through this antenna, and another is received through this antenna, okay? And after that, you have low noise amplifier, and then down converted into baseband, and signal goes to the breadboard, okay? And one thing I want to mention is very interesting. They did a very good job on the analysis of the link budget for the transmitter chain and receiver chain. So skip all those slides. Let's get started. Let's see. Yeah, right here, okay? So here, as we can see, it started from the voltage controlled oscillator, and the oscillator consumes a power of 0.25 watt, generates 6 dBm of signal. And after that, they have attenuator to attenuate a little bit. And now you have a smaller power, 2.7 dBm, right? And after that, you are talking about the amplifier here, okay? This amplifier further amplifies the signal into 16.7 dBm because after the amplifier, the splitter is gonna give you 3 dB more attenuation. Yes?
How would you attenuate an amplifier?
Why do we need this amplifier here, right? Is this your question?
No, yeah, why do you attenuate an amplifier?
Okay, that's a good question. So why do they do this? And personally, I don't think that is necessary. And if you look at their solution, the reason they do it is they just want that you have exactly 13 dBm of signal to drive your mixer, okay? And next, you have antenna specifications. After antenna, you have the receiver chain, okay? Receiver chain, what's important is if you look at the mixer is specified with different local oscillator driving power, okay? You need a specific power to drive the mixer so that the mixer is working properly, okay? And the authors here, they decided to use 13 dBm as the driving power, okay? So that might be one reason. And another reason is if you don't attenuate the signal, you have to make sure you are not pushing the amplifier into saturation. This we will learn in the future. No amplifier is ideal. If the signal power is too high, you're going to saturate your amplifier, right? Drive it into nonlinear region. So when you design this chain, you have to make sure everywhere the power is okay, you are not saturating things, okay? Does this make sense? All right, so eventually it turns out they have approximately 13 dBm of signal transmitted, and they have signal received, and in their model, they assume that there's about 50 dB of attenuation when the signal gets transmitted and bounced back, get captured by the receiver, okay? And for this design, they actually features FMCW operation, and in our homework, we have done some simple calculation on FMCW, right? For FMCW, you have to generate a linear ramp, which means the frequency increases linearly as time goes by. And this is really easy to do because they have this voltage controlled oscillator. And if you check out the curve for this oscillator, as you increase the tuning voltage, the frequency will also increase, right? So basically, if you generate a ramp signal as the tuning voltage, then your frequency is also moving in that direction. Yes? Tuning voltage means for the VCO voltage controlled oscillator, you have one terminal, control terminal, and that voltage controls the frequency of the oscillator. All right, any question? All right, but now you have seen one thing you can definitely improve. The performance here is lousy because this tuning curve is not linear, okay? As you can see, the curve eventually bends down, right? So if you have a linear chirp to control the VCO, the frequency will no longer be a linear chirp because this conversion, this transfer function is nonlinear, okay? So what you can do is you can consider maybe using a microcontroller to control the voltage, and you can make a lookup table to linearize the frequency. Does this make sense? This curve is not linear, but I can compensate for that. At higher frequency, I give the voltage a larger difference to bend it back to make it linear, all right? So that's another thing you can improve. You can make this smaller, you can make this more robust against interference and noise, and you can make the linearity better. And if the linearity is better, you probably can get a better range resolution, okay? All right, and finally, if you choose to do something like this, then we're gonna compare which one is the best among the designs. And the easy way is we're gonna set up an experiment. Maybe we're gonna put a target at 90 meters away from the radar, and you guys have to tell me what is the distance, because you can measure the range, right? And we're gonna use the error compared with the size of your radar, and also divide it by the power consumption, and that can define a figure of merit, okay, which is a fair parameter to compare among all the groups. Does this make sense? So try to make your accuracy, your resolution good, and try to make the size small, try to make the power consumption small. Okay? All right, any question? All right, if no question, then I'll see you on Monday. All right, thank you.